Hey guys, today we are going to be finishing the front page of our formula chart. So kind of talking about all of the rest of these subheadings. Now the very last subheading, the composite argument, we're actually going to spend some extra time on. But today we're going to be going over odd even, cofunction, and then the sum and difference properties. And our essential question is, how do I use trig properties to simplify expressions and prove identities? So it's kind of what we've been doing. It's just we're going to add a couple extra properties in. And again, you always get your formula chart, so this is nothing you have to memorize. And let's start. So we have the odd and even property. Basically, these properties are talking about what type of function you have here. So an even function, what happens is if you plug in a negative into your argument, when you get the answer, it's the same as you plugged in a positive. So for instance, if you had f of x equals x squared, if you plugged in f of negative 2 and you got that that was equal to 4, the same thing would happen if you plugged in that positive 2. So that's all that being even means. So for our trig functions, two of our functions are even, and they are cosine and secant. Okay, so evens go with cosine and secant. The other type is the odd types of functions. And what happens there, oh, hold on, I need to finish this example, that would help. So basically, when you have an even function, if you plug in a negative argument, all that you get here is that the negative drops. And you can think about that on your unit circle. If you found the cosine of negative 30 degrees, that horizontal distance is still a positive distance, and so it's going to give you the same ratio as the regular cosine of 30 degrees. Okay, so let's go back and now talk about the odd. So odd functions, what happens here is when you plug in a negative number on the inside, it basically makes it negative on the outside as well. And so the rest of our trig functions are going to be odd. So sine, cosecant, tangent, and cotangent are odd. And so what happens then is if you are taking the sine of a negative angle, that property tells me that I can just move that negative onto the outside and then take the sine of that positive angle, and it's going to give me the same answer. Okay, and so again, you don't have to memorize these. It even tells you right here that cosine of a negative is going to just give you the regular cosine, whereas sine of a negative is going to give you negative sine. Okay, so that's even odd in a nutshell. Basically, for an odd, the negative goes on the outside, and for an even, you get to drop the negative. Okay, the next type of property we're going to look at is the cofunction property. And the cofunction property, I remember this by remembering complement. And complementary angles, if you remember, add up to be 90 degrees. If you draw that C, and they make 90 degrees. So that's how I remember these guys. And complements, they all have that co in them. So sine goes with cosine. Cosecant goes with secant. Tangent goes with cotangent. And so that's kind of, I guess, why we use cosine instead of anti-sine or whatever. Okay, so basically what the cofunction property is telling you is that if you have the sine of 30 degrees, what you're looking at here is you can actually rewrite this, and that's what these guys are saying up here. If you remember, pi over 2 is equal to 90 degrees, because we're thinking about complementary angles. And so I can take this and rewrite this as cosine of 90 minus 30, and that would get me cosine of 60, because we're dealing with that unit circle. And you can prove this to yourself. If you found that sine of 30 degrees on your unit circle, you would know that opposite of 30 degrees is 1 over 2. And then cosine of 60 degrees, the adjacent side of that 60 degree angle is 1, and the hypotenuse is 2. So they are equal to each other. And that's just talking kind of about the phase shift of that sine and cosine function as well. So if I wanted to rewrite secant of 42 degrees in terms of cosecant, its cofunction, we would write cosecant of 90, since this is in degrees, minus 42. And we would know that secant of 42 is equivalent to cosecant of 48. Okay, works the same way for radians, it's just now we're going to have to use pi over 2 instead. So cotangent's cofunction is tangent. And then we're going to do pi over 2, which is 90, minus 3 pi over 8. This requires me to use a little bit of fractions going on here, but this would just be the same thing. Common denominator here would be 8 So this would be 4 pi over 8 minus 3 pi over 8. So we get that cotangent of 3 pi over 8 is equivalent to the tangent of pi over 8. Okay, and these are going to be really useful to use when we are proving identities again. So the last new thing we're going to talk about are the sum and difference properties, or the composite argument ones that are at the bottom of the page. Now we're going to start by talking why we can't just distribute the cosine through those parentheses. So if you look here, we're going to prove that cosine of a plus b is not equal to cosine of a plus the cosine of b. It's really quite simple to disprove something, because all you have to do is prove it wrong for one thing, and that means it's not going to work for everything. It's harder to prove something is true because you have to prove it's true for every single piece. So if I can think of one counterexample that's not going to work here, then I can show that this doesn't work. So I'm going to arbitrarily name an A to be 30 degrees because I like that angle, and B to be 90 degrees because I also like that angle. So if I plug in A and B here, I would have cosine of 30 plus 90 is 120 degrees. And if I found that cosine of 120 degrees over on the left side, remember 120 is going to be over in quadrant 2, and it has a reference angle of 60 degrees. So when I write my unit circle, I put out my ratios. This would be root 3, this would be -1. So the cosine of 120 would be adjacent over hypotenuse, and I would get that that left side is equal to -1/2. So now let's see what the right side equals to. Cosine of A would be cosine of 30, and we want to add it to the cosine of B, which is a cosine of 90 degrees. If I found the cosine of 30 degrees, remember I go in there and I do the opposite over, the adjacent over the hypotenuse, which in the first quadrant would get me positive root 3 over 2. The cosine of 90 degrees, if we think about 90 up here, that x value is 0, and so my cosine of 90 is 0. And now looking at this, -1/2 surely is not equal to root 3 over 2. They're not even the same sign. And so I cannot just distribute the cosine over those parentheses. This is a function in here, just like you couldn't say x plus y squared is equal to x squared plus y squared. No, because you've lost the middle term. Same deal here. Okay, and that is why we use these composite argument sum and difference properties. So I know these look tricky. You always will get your formula chart. And so the cosine of A plus B, we're actually going to be using this crazy formula instead of just adding across or distributing across the plus sign. Okay, so let's practice using these formulas. Again, make sure you have this formula chart out next to you so you can keep referring to it. They can be kind of tricky. So let's look at an example. So we have simplified the cosine of 34 degrees times the cosine of 20 degrees plus the sine of 34 degrees times the sine of 20 degrees. As soon as you see that you have matching angles in here, you know that we're dealing with some sort of composite argument type stuff. So if I look on my formula chart and I find one that has cosine, cosine, so I have cosine, cosine, and I have a plus sign in the middle, that means that I'm going to be using the cosine of A minus B. So I just write that as cosine A would be 34, and then minus B would be my 20. And now I can just do some math here. So this is cosine of 34 minus 20 is 14 degrees. Okay, so again, I said that this was the cosine of A minus B because I looked at my formula chart and I saw the one that had both cosines and then a plus sign in the middle was a minus. Alrighty, and so we are going to use these sum and difference properties in order to prove a couple more identities, prove some more statements. So basically these are going to end up being some exact value practices. So when I'm looking at the cosine of x minus pi, remember I can't just distribute over the parentheses. So I'm going to use my formula chart in order to expand this business and see if I can't make it equal over there to the right side. Remember, once you pick a side, you have to stick to it, and I think that this side looks a little bit more complicated. So if I look at my formula chart and I look for the cosine of A minus B, so x is going to be A and B is going to be pi. So cosine of A minus B says that we're going to take the cosine of A times the cosine of B, and then add the sine of A times the sine of B. Okay, so I've now expanded that left side out. Now if you remember some exact values here, we have that the cosine of pi, if you use your OIO chart or you remember your coordinates, so you'd be looking over here at pi, my x coordinate here is at -1. So I have cosine of x times -1. Okay, sine of pi, if I look at that same point, my y value is 0. So I would have sine of x times 0. So now I know that anything times 0 is 0, and -1 times cosine x would be -1 times the cosine of x, or negative cosine x. So I have proven that that is a true statement. Okay, so I looked on my formula chart, I expanded using that formula chart, so let's practice one more time. So cosecant of theta minus 90 degrees equals negative secant theta. Now the problem here lies in the fact that I don't have any sort of sum and difference properties for cosecant. I only have them for sine, cosine, and tangent. But remember, I can rewrite cosecant as 1 over sine of whatever argument. Okay, and so again, I'm going to pick my left side because it looks more gross and complicated, and then I'm going to go ahead and expand using that formula chart. So I now have the sine, and remember, 1 over this whole thing. I have the sine of something subtracted, so sine of A minus B, and A is going to be theta, and B is going to be 90. So using my formula, I'm going to have sine of theta times the cosine of 90, subtract, so minus cosine of theta times the sine of 90. And again, this is just some exact value practice because the cosine of 90 is a number. The cosine of 90 degrees, if I draw my coordinate plane, I know that that point is at 0, 1, so the x is at 0, so that's 0. And sine of that number would be 1. So this guy right here is going to cancel out, and I'm going to be left with 1 over negative cosine of theta times 1 is just cosine theta. And we remember our reciprocal identity, where 1 over cosine is actually equal to secant, and there's a negative in the front, and that's what I was trying to prove. So again, you can always use your formula chart. Please don't feel pressured to memorize these things. Sine and cosine with composite arguments can get a little bit tricky, but we're going to continue practicing using them tomorrow. So hope you have a great night.